a model-based controller can generate diverse dynamic motions for legged robots. Furthermore, it facilitates quick iteration to achieve desired controller behaviors, streamlining the design and test phases. However, it requires an accurate dynamics model of the robot, which is often unavailable. Consequently, these controllers typically underperform or may even fail to operate entirely when deployed directly on hardware. The discrepancy between models and actual hardware's behavior can be mitigated by carefully adjusting the control parameters. This tuning process is typically time-consuming. And more critically, it can harm the hardware platform. To safely tune the Locomotion controller, we employ a safe Bayesian optimization method. Our safe BO method trains a control gain tuner that adaptively adjusts the control gains. We begin the training from roughly hand-tuned control gains, which lead to significant vibrations and notable positional drifts. And we start the training process using data samples collected from hardware directly. Across 50 trials, we find the optimal control gains that minimizes joint-level tracking errors without breaching safety constraints. In this footage, we can observe significant joint vibration and foot slippage with the initial control gains. Our method effectively finds the optimal gains that remove the undesirable vibration or foot slippage. Different gait patterns have different optimal gains due to their distinct physical characteristics. As demonstrated in this footage, the optimal gains for trot pattern don't perform optimally for the new gait pattern, crawl. We extend our framework to generalize it over a diverse set of quadrupedal gait pattern by using contextual safe Bayesian optimization. Our method is able to find the optimal control gains for new gait patterns efficiently by leveraging information collected previously. Moreover, this approach enables fluid online adjustments of the control gains during operation. Furthermore, we demonstrate that our method improves the controller's ability to mitigate uncertainties. In the first test, we introduce external pushes to contrast the controller's resilience before and after the optimization process. Before the optimization, the controller struggles to withstand external pushes. However, after employing our method, the optimized gains enable the robot to effectively handle and overcome such disturbances. In the second test, we placed socks on the robot's feet to induce slipperiness upon contact. The initial control gains struggle and eventually fail because of the mismatch in the contact friction model. Meanwhile, the optimized gains successfully mitigate the model mismatch and enable the robot to recover from slips. Our method enables zero-shot generalization for the unseen gait patterns through a learned model. Although both flying trot and pronk were not presented during the training, the learned model effectively suggests reasonably good control gains for these gaits. Thank you for watching.